Hello, AP Chem kids. I'm going to be talking a little bit more about the gas laws. We didn't do this first year because we ran out of time, but basically we have some relationships between different components. So that's what we're going to be looking at and exploring and talking about. So the gas laws are named by different men. So there is Robert Boyle, Jacques Charles, Amadeo Avogadro, and Joseph Louis de Lussac. These are the guys who were doing some experimentation with gases and figuring out what was happening to the gases and the relationship. And in reality, it's pretty easy. You've already developed some of those relationships already through your travels and your findings. I'm going to be showing you some video demonstrations for things that we cannot do in class because we don't have them. And then tomorrow in class, we're going to be actually working on some of our own demonstrations that talk about which law, and you're going to have to tell me which law applies to the demonstrations that you're doing. And then we're going to talk about calculations, which are really quite easy. You should be able to get them. They're not as hard as you would think. Okay, so here's our first video, the balloon and the vacuum pump. So just watch the video. So the teacher places a balloon on top of something in a vacuum pump and puts a bell jar on top of it. While we have a vacuum pump, it is not working, and I don't have the parts that I need to get it to work. So we already turned it on. So observe what happens to the balloon. Now he releases the pressure. So what's happening in this whole vacuum pump scenario here is that when he puts the top of the bell jar on, you have atmospheric pressure because you have air molecules and other things there. And when he turns the vacuum pump on, it basically causes the stuff inside the bell jar to be sucked out. You're basically sucking all of the air out. So if you're sucking all the air out, what's happening in fact to the pressure that's going on in there? And the answer is the pressure is going down, because if there are no particles to push down, then there's little pressure. So vacuum is a situation where there is little to no pressure. So what happened in that situation when we saw the balloon as the pressure went down? What happened to the balloon? The balloon's volume went up. And then when we released the vacuum and let air back in, what happened? Well, basically the balloon went back to the volume it was. That means as pressure increased, volume decreased. As pressure decreased, volume increased. So we have a relationship developing there. So let's see what happens with PEEPs and the vacuum pump. Vacuum pump demonstrations are really cool.
Marshmallow. And a PEEP. On a clean plate. Put in a bell jar. Hooked up to a vacuum pump. Flip it on. Expand it as much as they will. So the vacuum pump at work. Here's the fun part now. Turn it off. Close the valve. Disconnect. Here we go.
is our peep marshmallow.
So why did this happen? So again, let's talk about the vacuum pump. What's the vacuum pump doing? It is sucking all of the air out of the vacuum, or all of the air out from underneath the bell jar, which means the pressure is going down. What happened to the volume of the marshmallow and the peep? By the way, a peep is pretty much marshmallow. It's just looks in the shape of a chicken, yellow. Now they're making Christmas tree peeps and egg peeps and God, there was a turkey peep, I think, at one point in time. So it expands and it gets bigger because as the pressure goes down, we know that the volume goes up. So then when we release the vacuum and we let air back in and pressure goes back up, what happens to the peep? Well, it goes down, but you're thinking, well, just like the balloon, it should stay the same size, right? But remember, what's marshmallow? Marshmallow is whipped sugar. Basically, we're whipping sugar and we're whipping air into it, and we're aerating the sugar. That's what gives the marshmallow its texture, that spongy texture. So once all the air is gone out of the marshmallow, because we've expanded it and all of the air has come out because the vacuum pump was taking the air out, we're left with something that is much harder than it was before. It's not so squishy as it was before. So just make sure that you understand that when we have food items that have air trapped inside of them, under a vacuum pump, they will expand. But once the air is gone from that trap, when we put the pressure back in, it will return to a volume that's actually smaller because the air is now gone. Unlike in the balloon, the air couldn't escape from the balloon, but the air can escape from the marshmallow and the peep. Okay? So next video, another vacuum pump video. So clearly we're talking about pressure volume here. Here we go.
My arm hurts. You gotta watch it.
Okay, I'm muting because the class is a little distracting. So what he has in here, inside the bell jar, he has a container of soda. And then on the outside of the jar, he has another container that he pours soda in, and he's using that one outside as a control group so that you can see what it looks like. Now, he just poured that. So you see they look very similar, but remember, he's got the vacuum pump running. So as the vacuum pump continues to run, you see more bubbles starting to form inside there. And now, if you look at the soda that he poured, there aren't nearly as many bubbles. So continue to watch and see what happens. So what's happening inside there? Well, it's soda. What is soda? Soda is a mixture. It's got gas in with the liquid, right? So the gas in with the liquid, the gas is coming out here because remember, we're pumping everything out. So you can say, well, isn't the gas filling the bell jar? Well, it is, but remember, the vacuum pump is pulling everything out. All of the matter is coming out of the vacuum pump. So as the gas escapes, it's escaping out of the vacuum pump as well. So it's going into the classroom in the atmosphere. Notice there are more and more bubbles, and the bubbles get bigger and bigger and bigger. Eventually, will the bubbles stop? Well, yeah, as soon as all the gas is gone, the bubbles will stop. But then what are you left with? Yeah, flat soda. And we know that we don't really care for flat soda. So, you know, we understand what's going on here and we see the whole process. We know that if we continue to do this, it will actually continue to boil because it will lower the, well, it's not really lowering the boiling point because it's in a vacuum. It will lower the boiling point of the liquid, the water. And so in a vacuum, your blood can boil because all of the gas escapes, and then your blood, because of the pressure, doesn't need as great a temperature to boil at. And so that's why in the vacuum of space, your blood would boil and you would pretty much fly apart. And so, okay, vacuum pump wonderfulness. So what does this have to do? Well, this is Boyles Law. Boyles Law basically states that pressure is inversely proportional to volume when temperature is held constant. What does that mean? Inversely proportional. It's not hard. As pressure goes up, what happens to volume? It goes down. As pressure goes down, what happens to volume? It goes up. So in every situation that you've seen here, you've seen that occurring in different ways. The curve over here to the side, this curve is representative of pressure versus volume, or volume versus pressure. And you notice it's a curve. It's an exponential curve. And you know how we love exponential curves? We hate them. We don't like them at all. So what we tend to do to straighten this out is we graph 1 over volume instead of volume. And then that gives us a more straight line relationship of these two things. So we do a lot of times in chemistry, we want straight line relationships because y equals mx plus b is wonderful. And we don't have to know any calculus or anything else to be able to solve that, okay? So let's go on to the next slide here. So the next slide is about Charles' law. Charles' law is a law about volume of a gas being directly proportional to temperature. And we've got to be really careful here because temperature is really important. We can't have negative volumes, so negative temperatures would give us negative volumes. So we always have to make sure that temperature in gas law problems are always in Kelvin first. Remember, Kelvin is pretty simple. You take the degrees Celsius plus 273, and that equals the temperature in Kelvin. Notice I didn't say degrees Kelvin, I just said Kelvin. I don't know why it made that crazy line right there. But there it goes. I got rid of it. Crazy line gone. All right, so that's how we get to Kelvin temperature. It's not degrees Kelvin, it's just called Kelvin temperature. And it's really important that we do that. Also notice that as temperature goes up, what should happen to volume? Well, it should go up. Now, I don't have any fancy demos to show you on videos because tomorrow we're going to be working through some videos that have to do with Charles' law. And they're actually quite fun. So you'll have a good time tomorrow working through some of that, okay? Next, the next video, I do not have a fire syringe, so unfortunately I cannot do this one for you, but you can watch it here.
Place a small tuft of clean, dry cotton into the chamber.
This is just a cotton ball. When they talk about clean, dry cotton, it's just a cotton ball.
Is the fuel. Attach the piston, screwing the top on firmly. Press down quickly to increase the air pressure. The increased air pressure increases the temperature, making it hot enough to ignite the cotton.
Okay, so almost finished here with this one, but what did you see happening? If you press down quickly, what you're doing is you're contracting, you're making it more pressure, just like we did with the closed syringe. We added more pressure to it. And if we do that quickly enough, what ends up happening is the gas inside there will increase in temperature. If we can do this quickly enough, we can get it to increase to a temperature that is greater than 400 degrees Celsius, which is the temperature that cotton needs to combust. So if we do this quickly, it's called an adiabatic expansion because we're doing it so that the temperature can't change. If we do it too slowly, then this won't happen because the temperature will dissipate outside. So remember, the heat inside, heat outside, it travels from high to low. And so because we do it quickly, we can get that done more quickly. If you do it slowly, you won't have that fire, that explosion, or that flame that bursts in. And all it is basically causing the cotton to combust because we're increasing the temperature of the gas molecules so quickly that it gets hot enough that the cotton will burn. We also pulled the cotton apart so that it would have more air inside of it. So that's a good thing too. So next video or next demonstration here, So this is Gay-Lussac's law. That's what pressure temperature changes are. And you can see pressure and temperature of a gas are directly related. That means as pressure goes up, so does temperature. As pressure goes down, so does temperature. They go in the same direction. You'll also notice that the way the equations are formed are different than Boyles' law. It's the same as Charles' law because it's a direct relationship. But you can see here that P1 over T1 is equal to P2 over T2. And if you look, that's the same as the slope of the line. Because if we take the change in pressure over the change in temperature, you get P over T. So straight line equations are really, really helpful for this. And if we look at the 1 over V over P, we'll understand that a little bit more, okay? So combined gas law, basically what did we do? We took all of the gas laws that we just talked about and we combined them into one. And this allows us to be able to use all of the relationships wrapped up into one. We know that pressure and volume are directly related. That's P and V next to each other. We know that volume and temperature pressure and volume are indirectly related. That's why they're next to each other. But volume temperature are directly related and pressure temperature are directly related. So now we can solve problems with all three. But remember, when we're solving, we have to know all but one. So anytime you're solving any of these problems, you have to know all but one of the variables. If you don't know two of the variables, you can't figure it out unless you have another way. So Avogadros Law. Avogadros Law is really, really simple, and I'm going to do a little demonstration tomorrow about this so that you can understand what it's talking about. But basically, it's saying that the amount of gas or the number of moles of gas is directly proportional to the volume of the gas. So when we look at that, and this is supposed to be a proportionality. I don't know why it's an A right now. It's supposed to be a proportionality sign. So V is directly proportional to N. That means the number of moles is directly proportional to the volume. So A is proportionality, V is the volume of gas, and N is the number of moles of gas. So what we get is the number of moles of gas is directly proportional to the volume. And so we get this relationship N1 over V1 is equal to N2 over V2. So we're going to stop right there. Sorry I went a little bit over, but I think you'll understand it tomorrow. We're going to have a little fun in the lab and do a little demo work. And you're going to be doing your own demos and kind of looking and exploring and doing some things like that. Okay? Thank you so much.